Diodes are unilateral devices. They exhibit direction-dependent properties. They allow current to flow from anode to cathode, but they don't allow current to flow from cathode to anode. This property, this nature is called rectification property. Diodes find several applications, but most important application is in rectification, in converting bilateral current into unilateral current, or converting a bipolar voltage into unipolar voltage. Diode applications, diode rectifiers, series on semiconductor devices and circuits, lecture number 2.15. Diodes are two-terminal devices. These are unilateral electronic devices. It means they exhibit properties which are direction dependent. Their resistance, their capacitance under forward biased condition is different from their resistance, their capacitance under reverse biased condition. If we consider resistance, it is very small under forward biased condition and it is very huge under reverse biased condition. This resistance property of the diodes, it is used for benefit in several applications, especially it is used in rectification. Rectification refers to a method by which bidirectional current is converted into a unidirectional one, or bipolar voltage is converted into a unipolar voltage. With this small introduction to rectifiers and diodes, now we move to the session where discussion is mainly on three basic rectifier circuits which use diodes in their structure. Now let us move further and start the session with some general points. Rectifier is an electrical device. It offers low resistance in one direction but high resistance in the opposite direction. Note here, direction refers to direction of current flow. As it exhibits low in one direction and high resistance in the other direction, it satisfies the condition to be called a rectifier. In fact, definition of rectifier is a device which offers no resistance for current flow in one direction and offers huge resistance for current flow in the opposite direction. Diode is exhibiting the properties that are required to be a rectifier. Hence, diode is rectifier. Diodes can be broadly classified into two types: ordinary diodes and special diodes. The ones that are used for general purpose, like rectification, clipping, clamping. Rectification means converting bidirectional current to unidirectional one. Clipping means a removal of a certain portion of the input waveform. Clamping means raising or falling a waveform to a certain voltage level. So rectification, clipping, clamping, all these techniques use diodes. Those diodes which are used in these methods, they are called ordinary diodes. Others, such as those used for signal generation, amplification, regulation, light emission, these are all called special purpose diodes. Tunnel diode is used in signal generation. Varactor diodes are used for amplification. Zener diodes are used for regulation. LEDs are used to emit light. These are all special purpose diodes. Large signal diodes and small signal diodes. This is another classification apart from general purpose and special purpose diodes. What are large signal diodes? These are diodes used to convert high voltage, low frequency signal into DC. Whereas the small signal diodes are used to convert low voltage, high frequency signal into DC. One point that strikes well into our minds is large signal and small signal. Both belong to the diodes used for rectification. So they are general purpose diodes. Large signal diodes, they are associated with the high voltages. Small signal diodes are associated with low voltages in converting AC into DC. Now, some more points regarding rectification. Conversion from AC to DC is accomplished in two steps. In the first step, bidirectional current or bipolar voltage is converted into unidirectional current or unipolar voltage using rectifier circuit. The input to the rectifier is pure AC and output is a mixture of AC plus DC. In the second step, the AC in the rectifier output is transformed into DC using filter circuits. The input to the filter is AC plus DC and its output is merely DC. Apart from rectifier and filter, there exists another part also in the conversion line of AC into DC. After filter, one can find a regulator. The purpose of the regulator is to maintain the voltage at a specific value irrespective of the current that is drawn from the supply. Now, let us concentrate on the first part of the power supply, that is conversion from bidirectional current or bipolar voltage into unidirectional current or unipolar voltage. That is the subject matter of the present session. Rectifier circuits are available in three varieties. Depending upon our requirement, we can go for either one. What are the three? Half wave circuit, full wave circuit, bridge circuit. Half wave circuit uses one diode and a transformer. Full wave circuit uses two diodes under a center tapped transformer. Bridge circuit uses four diodes and a transformer. So as you move from half wave to bridge, number of diodes employed in the design, this number is increasing from 1 to 4. In half wave circuit and in bridge circuit, transformer is used, but in full wave circuit, center tapped transformer is used. Center tapped transformer is a little expensive when compared to ordinary transformer. Some more points regarding half wave circuits. They give AC plus DC. Full wave circuit also, output is AC plus DC. Bridge circuit also, it is AC plus DC that exists at the output terminals. But in half wave circuit, DC is low. In full wave circuit, DC is high. In bridge circuit also, DC is high. As DC is low and rectifier circuit is there to give DC, one can say half wave circuits are crude when compared to the remaining two circuits. Some more points, general points. In the analysis, the diode is assumed to be semi-ideal. It acts as open circuit on reverse bias and a small resistance RF under forward bias. This is diode under ideal conditions. It is supposed to be short circuit under forward bias, open circuit under reverse bias. In the analysis, we are going to do in the present session, we assume the diode as open circuit under reverse bias, but not short circuit under forward bias. We assume the diode as a resistor having small resistance RF under forward bias. In the discussion which we are going to have in the session, we encounter three types of waveforms: full sinusoidal wave, half rectified wave, full rectified wave. Full sinusoidal wave is a pure AC with no DC. Half rectified wave, it is associated with a large AC, small DC. Full rectified wave is associated with small AC, large DC. For better understanding, I sketch all the three waveforms. This is full sinusoidal wave. Then half rectified wave. How it appears? It appears like this. This is a half rectified wave. Full rectified wave, how it appears? This is full rectified wave. Now, with the diagrams in place, we can have a better idea regarding the shapes of the waveforms. One or two points require to be mentioned right now. In case of first one, full sinusoidal wave, the RMS value is AM by root 2. RMS value or AC value. DC value is of course 0. Here AM is amplitude of the wave. When it comes to half rectified wave, RMS value is AM by 2 and DC value is AM by pi. When it comes to third waveform, RMS value is AM by root 2 and DC value is 2AM by pi. In all these expressions, AM refers to amplitude of the wave. These values requires to be in the background in our minds while we are going to understand the functioning, the analysis of rectifier circuits. Input to all the rectifiers is pure AC. First one, full sinusoidal wave. Full sinusoidal wave and the output is full or half sinusoidal. Input to rectifier is given through a transformer and its output is connected to load through a filter. Average or DC value of waveforms indicate the DC component, or for a good rectifier, it should be as large as possible. Now, A few points regarding performance of rectifier circuits. It has already mentioned that there are three basic rectifier circuits. Out of the three, which one is better? Which one is inferior? What is the basis? All these aspects require to have performance indices. In this case, in the case of rectifier circuits, several indices are there. Those indices are mentioned in the present slide. First one in this lot is efficiency of rectification. By definition, it is the ratio of DC output power to AC input power. Note, efficiency means output to input. Here it is DC output power to AC input power. Transformer utilization factor is another performance index. The ratio of DC power output to the volt ampere rating of the transformer. It is transformer utilization factor or TUF, TUF, TUF or TUF. Another parameter index of great importance in describing the performance of rectifier circuits is percentage regulation. By definition, it is V no load minus V full load by V full load into 100. 100 is there because it is percentage. Notice here it is not visible. V no load refers to V DC no load. V full load refers to V DC full load. No load or full load voltages, they pertain to DC voltages at the output terminals. One more point is regulation can be up, regulation can be down. Here the regulation is down regulation. Another parameter is ripple factor R. By definition, it is RMS value of AC components of waveform to average value of waveform. This ratio, by definition, is ripple factor. It is equal to IRMS by IDC whole square minus 1, everything under square root. Form factor as an important parameter. It is ratio of IRMS by IDC peak factor, peak value to RMS value. Don't confuse peak factor with the form factor or form factor with peak factor. They are different. Now we give comparison of the three rectifier circuits. In case of half wave rectifier circuit, ripple factor is 1.21. For full wave circuit, it is 0.482. For bridge circuit, it is 0.482, same as that for full wave rectifier. Notice, for full wave rectifier, for bridge rectifier, it is 0.482, far lesser than that of half wave rectifier, which is 1.21. It implies DC is more in full wave rectifier and bridge rectifier when compared to AC, and it is DC is less, AC is more in the output of the half wave rectifier when compared to full wave or bridge rectifier circuits. Another parameter, percentage regulation. For half wave rectifier circuit, it is given by RF by RL into 100. RF means forward resistance of diode, RL is load resistance. For full wave circuit, rectifier circuit, it is RF by RL into 100. For bridge circuit, it is 2 RF by RL. Percentage regulation is same for half wave and full wave rectifier circuits, but it is double to bridge rectifier circuits. Now we move to another performance index, efficiency of rectification. It is equal to 40.5 by 1 plus RF by RL. In case of a half wave rectifier circuit, it is double for full wave rectifier circuit of that of half wave rectifier circuit. For bridge rectifier circuit, it is the same as that for full wave rectifier circuit. Now let us move to see the actual circuits. We start with the half wave rectifier circuit. In this slide is shown the actual circuit. Notice here is a transformer. Two lines are there. These lines indicate the transformer is an iron core one. Iron core transformers are used in rectifier circuit for the reason that they occupy less space. Primary of this transformer is connected to AC input. Output of the transformer, secondary of the transformer, is connected to load through a diode. Usually, the purpose of the transformer is to step down the voltage. Input may be 230 volts. It is stepped down to maybe 100 volts or 80 volts. Voltage amplitude gets reduced by the transformer here. So it is a step down transformer. Except that difference, output of the transformer is same as input to it. Only amplitude becomes less. The output can be sketched, and when sketched it appears like this, sinusoidal. Of course, it is assumed that the input, AC input, is sinusoidal. Hence, output of the transformer is also sinusoidal like this. One cycle is shown. After this cycle, another cycle, another cycle, another cycle, like that. Cycle after cycle continues at the output terminals. Now, one or two points regarding the functioning of the half wave rectifier circuit. This waveform, one can see it is pure AC with no DC. This waveform can be seen as consisting of two half cycles, one positive half cycle, another negative half cycle. During positive half cycle, what happens is the anode of the diode is positive when compared to cathode. Therefore, the diode starts conducting. So this entire voltage, positive half cycle with amplitude Vm, it gets applied across RL. If forward biased diode resistance is 0, usually it is not 0, it is already mentioned, it is RF. So a small portion of the positive half cycle appears across the diode, remaining majority of the voltage appears across RL. The result is flow of current. Current flows during positive half cycle. That current is sketched here. During negative half cycle, anode of the diode is negative when compared to cathode of the diode. Therefore, diode is under reverse biased condition. It becomes a open circuit. Entire voltage that is applied across the rectifier circuit by the transformer secondary, it appears across the diode, across the open circuit, and no current flows. Therefore, voltage across RL is 0. So current is 0 during negative half cycle. The current is shown as 0 in the negative half cycle. Of course, voltage across RL also becomes 0. After negative half cycle, another positive half cycle starts coming up. During that positive half cycle, again current flows. That current can be seen same as the current which we got during the first positive half cycle, like this. Here also another positive half cycle. Now notice input is AC, but output is, it is not pure AC. It is a combination of AC plus DC. DC value one can easily see, DC value is Im by pi. So DC is there here. Input is pure AC, output is DC plus AC. Now we can conclude that half-wave rectifier is able to convert pure AC into DC. Of course, AC is also exists. Some parameters. Maximum current in the circuit is I. Maximum value for I is, it is designated as Im. It is equal to Vm by Rf plus RL. DC current in the circuit, it is Im by pi. RMS current in the circuit is Im by 2. DC voltage across the diode, it is minus IMRL by pi. DC voltage across the load is IMRL by pi. Of course, first one, it is quite easy to understand. Input voltage is like this. If this is Vm, naturally current is voltage to resistance ratio. This is voltage, maximum value or amplitude. Resistance in the circuit is Rf, RL. We are focusing on maximum current. During positive half cycle, only current flows. During negative half cycle, no current flows. So we need not worry about current in the negative half cycle. Our focus entirely just requires to be on positive half cycle. Maximum value of voltage is Vm. Resistance in the circuit is Rf plus RL. Regarding Im by pi, Im by 2, please recollect, for half rectified sine wave, DC value is Im by pi. RMS value is Im by 2. From this, these expressions have come into being. Some more points regarding half-wave rectifier circuits. PIV, peak inverse voltage, is equal to peak transformer secondary value. What is peak inverse voltage? Here it means maximum voltage or highest voltage that appears across the diode under reverse biased conditions. That is peak inverse voltage. If this voltage happens to be very high, then diode may not be able to withstand such a higher voltages, and it may result in breakdown. So we have to see that while designing the rectifier circuit, whether the diode is able to withstand the voltages that appear across it under reverse biased conditions. Of course, under even forward biased conditions also, we have to see whether the diode is able to cope up with the maximum voltages that appear across it. Now, regulation. Regulation indicates variation of DC output voltage with the DC load current. By definition, it is V no load minus V full load by V full load into 100%. It is already mentioned earlier. For an ideal half-wave rectifier, percentage regulation is 0. In case of practical half-wave rectifier circuit, it is equal to Rf by RL into 100%. Notice when this regulation becomes 0, when Rf is 0. Rf 0 means under forward biased condition, the diode is short circuit. Diode is now ideal. So half-wave rectifier circuit which uses ideal diode is ideal half-wave rectifier circuit, and its regulation is 0. Another parameter of importance, great importance when it comes to rectifier circuits is ripple factor. By definition, it is the ratio of RMS value of AC components of the wave to the average value of the wave. It is equal to I prime RMS by IDC, V prime RMS by VDC equal to IRMS by IDC whole square minus 1. This is all under square root. Notice in this expression, I prime RMS is there. Here it is IRMS. These two are different. I prime RMS refers to RMS value of AC components of the wave. V prime RMS refers to AC components, RMS value of AC components of the wave. Whereas IRMS here without prime, it refers to simply RMS value of the output of the rectifier. In case of half-wave rectifier, ripple factor is 1.21. One can apply this definition to find out ripple factor. It turns out to be 1.21. Now we move on to another rectifier circuit, that is a full wave rectifier circuit. The circuit is shown here. Here also there is a transformer. Primary of the transformer is connected to AC input. Notice this transformer is a center tap transformer. Two diodes D1, D2. Load RL. It is connected here. The functioning can be understood without much difficulty. It is like this. Input to the rectifier is full sinusoidal wave. It is transformed into two voltages with a center tapped transformer, and these two voltages are exactly equal with amplitude Vm. So voltage that appears in the upper half of the transformer, voltage that appears in the lower half of the transformer on secondary side, they are exactly same because of this tap at the center, and let us suppose their amplitudes are Vm. So let it be Vm, this one, Vm. Now, first we consider a cycle, one cycle, full cycle. This cycle has two half cycles, positive half cycle, negative half cycle. During positive half cycle, what happens? In the upper half, D1 anode is positive when compared to its cathode. Therefore, D1 starts conducting. So current flows like this through load. During this same half cycle, positive half cycle, notice in the lower half of the transformer secondary, D2's anode is negative. Therefore, D2 becomes reverse biased. So it acts as a open circuit. Therefore, no current flows. I2 is 0 through D2. Hence, during positive half cycle, D1 conducts, D2, it goes to half. During negative half cycle, anode of D1, it is negative, so D1 goes off. Whereas, anode of D2, it is positive. It starts conducting. Now, current starts flowing through D2, that is I2, and it flows through load. So during positive half cycle, as already mentioned, D1 on, D2 off. During negative half cycle, D2 on, D1 off. In the next cycle, again during positive half cycle, same sequence of events repeat. When D1 or D2 is conducting, current through load is equal to voltage that appears across half of the transformer secondary divided by resistance of the diode plus resistance of the load. As input voltage is varying sinusoidal manner, current also varies sinusoidal manner. So one can sketch I1 is current through diode 1. It is like this. I2 flows during negative half cycle. It is like this. I2. I is current through load. It is actually I1 plus I2. When one sketches I1 plus I2, it appears like this. Full rectified sine wave. Before going further, notice input is pure AC, but output means output voltage across the load or current through load. This current through the load, you can see it's a DC. It is not zero. Input is pure AC, implying no DC. Output is having certain amount of DC. Of course, AC also exists. So we can say this is circuit, full wave rectifier circuit with the center tap. It is able to convert AC into DC. Of course, this conversion is partial. Certain parameters pertaining to full wave rectifier circuit. Maximum current is Vm by Rf plus RL. Usually it is indicated by Im. DC current is 2Im by pi. RMS current is Im by root 2. DC voltage is 2Im RL by pi. Power input to rectifier is I square RMS Rf plus RL. Notice DC current in the load or DC voltage across the load. These are higher than the quantities, corresponding quantities of half wave rectifier circuit. Therefore, one can say full wave rectifier circuit gives better performance when compared to half wave circuit. Peak inverse voltage in case of full wave rectifier circuit is twice the maximum transformer voltage measured across the midpoint to either end. The importance of PIV has already been explained. Percentage regulation in this case is Rf by RL into 100. Ripple factor is 0.482. It is far lesser than that of half wave rectifier circuit. It implies that AC in the output of the full wave rectifier circuit is smaller when compared to that in the output of the half wave circuit. Full wave rectifier circuit is associated with two shortcomings. It requires a center tap transformer. Of course, center tap transformer is expensive when compared to ordinary transformer. Second shortcoming is only half of the transformer output voltage is utilized for rectification. During one half cycle, one half is used. Remaining half of the transformer, it is idling. So it is a wastage of resources. Now we move to another rectifier circuit. It is bridge rectifier circuit. The circuit is shown in A. Here also a transformer. Lines must be there. As I already mentioned, lines indicate that the transformer is an iron core 1. Iron core transformers, they occupy less space. It is an advantage. Usually, for this reason, iron core transformers are used in the design of rectifier circuits. Input is given here. It is usually stepped down and appears at the secondary. This Vi, as usual, it appears like this because it is pure AC, and here we assumed that it is sinusoidal. This is Vi. Notice here is a bridge. This bridge is made up of four sides and 4 diodes. In each side, there is one diode, D1, D2, D3, D4. And the load is connected across two terminals. Input is connected across the other two corners or terminals of the bridge. Now, regarding the functioning, we consider one cycle. Let us divide this cycle into two: positive half cycle, negative half cycle. First, consider positive half cycle. During positive half cycle, A is positive, C is negative. When A is positive, D1 becomes on, forward biased, and also D3. So D1, D3 both become on and current flows. The equivalent circuit is shown here. Current flows like this through the diode like this. D1, load D3. The current, the resultant current is sketched here, I1. During negative half cycle, C is positive, A is negative. As a result of that, D2 becomes on and also D4. So D2, D4 both become on and current flows through D2, load, and D4 like this. The circuit is shown here. I2, when sketched, it appears like this. Notice I1 and I2. I1 is the current through load during positive half cycle, and I2 is the load through the load during negative half cycle. Okay. But the point to be noted here is I1 and I2 both are in the same direction. In B, notice I1 is from top to bottom. In C, notice current is again from top to bottom. So direction of current is the same. Similarly, in the next positive half cycle, I1 exists. Next negative half cycle, I2 exists. The current through load is I1 plus I2. When we add I1 and I2, we get like this, which is shown in D. This waveform which is appearing in D, notice it is same as the waveform at the output terminals of a full wave center tapped rectifier circuit. Certain important parameters, values pertaining to bridge rectifier circuit. Maximum current is Vm by 2Rf plus RL. Why 2Rf? Reason is while conducting either positive half cycle or negative half cycle, always there exists two diodes in the circuit. Their resistances added makes the resistances of the diodes plus RL as 2Rf plus RL. So this 2Rf is resistances of the diodes, two diodes which are in the circuit when current is flowing. DC current through the load, it is 2M Im by pi. RMS current is Im by root 2. DC voltage across the load is 2 Im RL by pi. Power input to the rectifier is IRMS square 2Rf plus RL. Some more points. Peak inverse voltage is peak transformer secondary voltage. Regulation is, it is can be found from this relation VDC equal to 2 Vm by pi minus 2 IDC RF. This relation is useful to find regulation, or this particular relation given here, it is able to give much information, lot of information regarding regulation. Rectifier ripple factor is 0.482. So AC here in the circuit is low. It is suitable for high voltage application. Summary is mentioned in this slide. Maximum load current, it is Vm by Rf plus RL for half wave rectifier. It is the same for full wave rectifier. It is Vm by 2Rf plus RL in case of bridge rectifier. Average load current, it is Im RL by pi for half wave rectifier. It is double For full wave rectifier, it is same as full wave rectifier for bridge rectifier. Effective load voltage is IMRL by 2. For half wave rectifier, it is IMRL by root 2. For full wave rectifier, it is IMRL by root 2 for bridge rectifier. So for full wave rectifier and bridge rectifier, effective load voltages are same. Efficiency of rectification 40.5 by 1 plus RF by RL. In case of half wave rectifier, it is 81 by 1 plus RF by RL. For full wave rectifier, it is 81 by 1 plus 2 RF by RL in case of bridge rectifier. Percentage regulation RF by RL into 100. Half wave rectifier circuit, it is the same for full wave rectifier circuit. It is double in case of bridge rectifier circuit. Ripple factor is 1.21 for half wave rectifier circuit. It is 0.482 for full wave rectifier circuit. It is 0.482, same as full wave rectifier in case of bridge rectifier circuit. Form factor is 1.57 for half wave rectifier circuit. It is 0.55 in case of full wave rectifier circuit, and bridge circuit it is the same 0.55, same as full wave rectifier circuit. Peak inverse voltage is Vm for half wave rectifier circuit, 2 Vm for full wave rectifier circuit, it is Vm for bridge rectifier circuit. Peak factor is 2 for half wave rectifier, root 2 for full wave rectifier, it is same for bridge rectifier. Transformer utilization factor TUF, it is 0.287 for half wave rectifier circuit, it is 0.691 for full wave rectifier, it is 0.812 for bridge rectifier circuit. With this, we come to the end of the session. To conclude the session, let us recollect a few important aspects that are touched upon in this session. This particular session is basically meant for introducing rectifier circuits. All the three basic rectifier circuits, half wave circuit, full wave circuit, and bridge circuit, all the three are introduced. Their comparison is also made with respect to performance indices of rectifier circuits. Hope this session is useful to you. We meet again soon with a new topic.